Hello, and welcome to the first lesson of Unit 1, Lesson 1.1 on function notation and domain and range. I changed it a little bit up from last year, just a little. It's still mostly the same, but I changed it some to give us a little bit more time discussing what a function is, getting very comfortable with function notation, and these different ways we're going to express domain and range. Okay. So, if you missed class, or if you just need to catch up, just look at it again, right? That's the purpose of this video. So, we start with, right here, what is a function? So, I say below are given two sets, A, which is this collection of items here. You see, notice A is called a set, and a set is denoted with curly brackets like this. This is going to be important later. So A is the set of numbers 1, 7, 3, 12. That's not a sequence necessarily. It's just a collection of numbers, just floating in space. B is also this set, 9, 21, 36, 3. And our goal is to pair each element of the set A with exactly one element from the set B, such that we have a consistent mathematical relationship between the numbers. And we'll just draw arrows from A to B to represent our pairings. And so I gave people class time to work through this. If you'd like to pretend like you're in class and try it out for yourself, you're welcome to pause the video and do so. But I'm just going to go ahead and kind of do it. So actually see, okay, I got one, and then I'm looking at these, right? Look at 9, 21, 36, 3, and maybe notice, well, all of those seem like multiples of 3, right? There seems to be a commonality here. And so we could draw a mapping. This is called a mapping, if you want to write that down, a mapping. And that's when we draw arrows between these things, right? Something like this. Anyway, so I might say, okay, let's map 1 to 3, right? Let's map 1 to 3. Let's map 7 to 21. And we'll map 3 to 9. And we'll map 12 to 36, like so, okay? And you might say, well, why did we choose to do this, right? Maybe it's obvious, maybe it's not. I've sort of noticed a relationship of tripling the numbers, right? Like 1 times 3 is 3, 7 times 3 is 21, 3 times 3 is 9, and so forth, right? So that's kind of my rule that I've made up, right? The elements in the set B are triple of what the elements of the set A are. So if I come here and I read this sentence here, right? Let A be some arbitrary element in the set A. Before I continue reading this sentence, arbitrary element, what does that mean, right? Well, element just means it's a number in here. Arbitrary, the definition of arbitrary would kind of be something like, does it matter, right? Or maybe in the context of math, you might think of it as, it doesn't really matter what you choose. It could be anything, yes? Arbitrary means it just comes from the set. We don't really care what it is. And then we'll let B be another element in B. Notice, right? Little a, and then in capital A, and little b in big B. And we say, write a rule or an equation that relates B with A. So I would say, okay, look, little b is from the set B. And we said that all of these numbers are just triple of something from A. So it's like if you take something from A, right, an element from A, then I multiply by 3. And that gets me B. Or you could say, right, B equals 3A, 3 times A. Whatever, doesn't really matter. And that is the relationship between these two sets, right? Now, what I'd like to say and mention is this is not the only mapping you can create. And this is the power of functions. Yes, we found a consistent relationship between the numbers, but there's no right or wrong answer here. If you chose to pair 1 with 9, 7 with 21, 3 with 36, and 12 with 3, that's valid. Actually, we can create functions like that. And when we say function, your experience in Algebra 1, and it's going to be the same experience in Algebra 2 as well, we're usually going to define it with some sort of equation to relate them, but the deeper you get into mathematics, you realize that functions really just are mappings. And it doesn't matter like how you map it, as long as there's some sort of rule or something that kind of gives guidance as to how that mapping occurred. Anyway, I'm not going to spend any more time explaining that. I just want you to get the idea that that's a function. Okay, so some definitions. What is a function? Well, I kept saying it, right? A function, f, is a relation, right? A relation, sometimes it's called a rule. So I might actually say, if you want to write rule here, you could do that, but I'm not going to keep that in notes. So a function is a relation between two sets, A and B, that assigns each element A in A to a unique element B in B. You say, what? Huh? What did he say? Okay, let's break this down. I'm giving you the formal definition of a function because we're in Advanced Algebra 2. We're building our vocabulary, our definitions, and the way mathematicians talk, right? So this little thing right here, maybe you've seen this before, maybe not. What does that mean? Well, the little a is just some element of the set A. When I say element, that's what that little epsilon is, right? That little guy right there is called epsilon. That's what that symbol's called. We have a table group named after epsilon, all right? And what epsilon means as a symbol like that just means in or part of. Or I think I like the most belongs to. All right? All of those work. You say in, it's part of, or it belongs to. Maybe the exact word is element of. Right? So you say A is an element of capital A. So it just means it belongs to that set. So anyway, that's all that little epsilon symbol means. Don't worry about it too much. Okay? And then notice I go here and I say a unique element, B and B. Now, what do we mean by unique? And we're going to see this word a lot in our math vocabulary. You might think, okay, what's the definition of unique, right? Well, it's different. It's different from everybody else. In mathematics, unique, right? It means exactly one. That is what unique means. Notice how earlier, when we come up here and we have, you see how the conditions were match one pairing, right? Exactly one. So that's the idea, is that if I choose an element from A here, I'm only going to draw one arrow, okay? Don't draw two arrows mapping to separate things, because that's not the definition of a function. A function is I have one number, and I map it only to a specific one element, a unique element, okay? Okay. That's what's meant by uniqueness. Okay, now the set A, right? Because you see what the function is doing, and I guess I neglected to draw this up here. What's going on is I've got A here, I've got B here, and what F is doing, or I call it F, F is for function, F is the mapping from A to B. And so that's what I draw here, right? It's the relationship between these two sets. So that first set, A, we call that the domain of F. You've heard that word before, right? The domain is the set of inputs. That should sound familiar from Algebra 1, I hope. If not, no worries. We're reviewing, right? We say that A is the set of inputs for the function F. And then the B, and you might be saying, hey, domain and range, right? So I actually call the set B is called the codomain. That's perhaps the official name of it, but colloquially we call that the range, okay? We call that the range of F. But you may see this word, okay, codomain. Right, codomain. All right. And that's the range. I mean, the range is the set of outputs. Beautiful. All right. And then we got function notation. Okay. Did I miss anything? I think we're good, right? F maps A to B. And as a little aside note, this isn't even the full way to write it. I should be writing this. You might say, what? This just establishes that F is a function, And then I establish what my domain and range are. But don't worry about that. Don't worry. Okay, don't worry. No sweat. I'm not writing it like that. Okay. Anyway, function notation. How do we read these things, right? So I'm going to write this. I'm going to say f parenthesis x, and I might ask you, how would you say this out loud, right? How do you say this out loud? Well, I want you to think about that, and then pause. You don't actually have to pause the video, just pause as I have just now. And I want you to consider this. A parenthesis B. I want you to think, how would you pronounce that, right? And is there a difference, right? I say F parenthesis X versus A parenthesis B. Is there going to be a difference in the way you say these things out loud? Now, assuming you've taken Algebra 1 and you're totally with this and you remember stuff about functions, you're probably going to say that f parenthesis x is called f of x. And you would be right? Let's say f of x. But would you say a of b here? Or would you say a times b? Right? Is it a times b? Or is it a of b? And that's the question, right? Well, it is dependent on context. So the thing is, one of the biggest things that first-time Algebra 1 students make, it's a big mistake they make, when they're first introduced to this notation, they call it f times x. And who knows, maybe you're still doing this. If so, it's okay, but time to change that, practice, all right, and adopt this f of x vernacular. It's not f times x. Because function notation, while it looks like multiplication, right? Because, right, a times b, hello, that's fine, right? That's parentheses. Parentheses mean multiplication, but they also play a factor in function notation. Here's how I like to think about it. How do you say this word? If you think about it, right? Or actually, I think I like this one even better. I like that one. How do you say this word? And the way you pronounce it, well, you could go about it two different ways. Because if I say this, how would you say that sentence? You say, I lead the group. But what if you said this? You would say that's full of lead, right? And so you say, well, how do I know how to pronounce this word? Well, you could pronounce it lead or you could pronounce it lead, but the way I'm going to know is thinking about the context I'm seeing the word in, right? Usually, f represents a function. And so that's when you see f of x, we say f of x. But if I say a is a function, if I say that, and I do have a of b, I could say that. I can say a of b. So the thing about function notation is we're always going to establish that that's a function. You're always going to be given a question, a problem, or something like that. It's going to state it. It's going to say something like, let f be a function, or define f of x to be this relationship, okay? Anyway, so function notation, I just wanted to clear that up. You may have known that already, but I find that few teachers ever really take the time to explicitly explain why we say f of x, yeah? And it's context dependent. I don't know, maybe it's not few teachers. Maybe that's just a wrong assumption on my part. I don't know. Anyway, in labeling this, f of x, you see f is the name of the function. You've given the function a name, f. X is the input into the function. Remember, the domain is the set of inputs, and usually x is the input and y is the output, right? But not always, and it doesn't have to be. And let me lasso this. Oops. Lasso this and move it down. The thing about f of x, this fella, that's nasty. f of x itself, so not f, not x, but f of x as an item, the whole thing, that's the output. You see, because what you do is you take x, you apply f to it, and it spits out f of x, or we know that as y. Okay? F is the relationship between those things. Anyway, so let's look at a few examples of function notation. Here's the one I did in class. I said f of x is the square root of x plus 3. I have defined this to be a function. And if I want to be really formal, I would say let f be a function such that f of x is equal to square root of x plus 3. But I'm not going to write that here. That would take just too much time. So what does it mean to evaluate f of 4? What does that mean? Well, x is the input, right? F is that function, but the 4 is the input. And what am I inputting? I'm inputting 4, but into what? Into f. And f is this relationship, right? It's this equation. So I'm going to say, all right, f of 4 is the square root of 4 plus 3, right? Because x was the input, right? This was some element of the domain, and I'm choosing 4, so I put 4 in. Now, it's very easy to evaluate this, right? What's the square root of 4? We say it's 2. We do 2 plus 3, we get 5, right? Okay, fantastic. Let's look at another. Let's say f of negative 2. So what's that? Well, if f of x is square root x plus 3, and f of 4 is square root 4 plus 3, then f of negative 2 will be square root negative 2 plus 3. And I do caution you to be careful. We haven't totally talked about all the rules with square roots, because we're really going to dive deep into square roots in Algebra 2. I can't combine this. Some students might be inclined to say that that's equal to 1, because you might be thinking, oh, well, it's the square root of negative 2 plus 3, so that's like the square root of 1, which is 1. That's not true. Okay, so if you were thinking that, it's okay, but that's not true. We can't add that. The 3's not under the root symbol, so that doesn't work. So we ask ourselves, well, we knew what the square root of 4 is because 4 is a perfect square, right? If I make a literal square with area 4, I get a nice whole value, an integer, 2 and 2 as the side lengths, right? 2 times 2 gets me 4 and makes a perfect square, right? If I made a square of 25, the side lengths would be 5 and 5 to make that happen, right? But the question is, if I have negative 2 as my area, well, what times what is negative 2? And it has to be the same number. You'll find that there's no real number that works. And I do emphasize real. There is a non-real number that works, but we're going to be touching that later in the year. So don't worry too much about that. For now, can I take the square root of a negative number? No. Right now, in this time, no. So actually, we say DNE, which means does not exist. All right? Oops. Okay. Boop, boop. Does not exist. Okay. Because square root of negative 2, it's not a real number. So I can't actually end up evaluating that. Okay, let's do another one. How about f of k? What is that? Well, if f of x is square root x plus 3, and f of 4 is square root 4 plus 3, and f of negative 2 is square root negative 2 plus 3, then f of k would be the square root of k plus 3. And that's it, right? Are you noticing a pattern here? Yeah, we're just replacing x with whatever is in those parentheses, yeah? The general gist, I like to do this. I say, what is f of pigeon? Yes? What is f of pigeon? I say, well, the input is pigeon, so that's like our x, so it's the square root of pigeon plus 3. Yes, Absolutely. That's perfect, right? F of pigeon is square root pigeon plus 3. We can get it even more complicated. We could say, what is f of t plus 1, right? Well, if you just view t plus 1 like you view the pigeon, it's the square root of t plus 1 plus 3, and that's it. And so I hope by seeing this over and over and over again, you just see that whatever's in those parentheses, that's wherever you see x in the equation, you're replacing it. Okay. Moving on, second page, writing domain and range. I'll try to be quick with this. I took a long time explaining this in class, and I don't think I needed to. So writing domain and range, there's really 3 ways, okay? There's inequality, there's set notation, and there's interval notation. You are very familiar with inequality notation, or at least you should be. Let me work through an example and show you kind of how all it goes. So I'm going to take this first one here, okay? I'm going to start this. 5 is less than h is less than or equal to 10, okay? What does this mean? What is h and where does it belong? Well, I'm going to create a number line here, like so. Here's my number line. And I say, okay, h is some number. H is a variable, right? And the conditions are, I have 2 things. I say h is less than or equal to 10, but I also see and, right? H is also more than 5. And you see that right here, right? So, for example, can you think of a number less than 10, but also more than 5? Yes, right? 6, 7, 8, right? So look, here's 5, here's 10. You know that 6 works, you know that 7 works, and 8 works, and 9 works, and even 10 works because the condition is it can equal 10. 5 does not work because it's not equal to 5. So what I'm going to do, I'm going to shade in this whole little region here, okay? I'm shading. All right? All of that is h. And because it's equal, it includes 10. And so I'm going to use a big little dot here that's nice and filled in to show that this does include 10. It's equal to 10. However, it is not equal to 5, so I'm going to use an open dot like so. And so the difference is a filled in dot, right? We call this inclusive. Inclusive. So signs you're going to see are less than or equal to or greater than or equal to. If it's equal, that means it's part of it. Equal means is, right? So it's part of it. It's part of the set. An open circle, like so, we're going to call this not inclusive. Okay? And that's going to be signs like strictly less than, strictly greater than. They're not equal, right? And so the idea behind non-inclusive, right? If h, I've got this 5 here, and then it's all this other stuff. What could h be? Well, h could be 4, h could be 4.5, h could be 4.9, 4.99, 4.9999999, right? But not 5. Make sense? So it gets close to 5, it just doesn't actually include 5. All right. This is inequality notation. So that's inequality. Oh, let's lasso that. And hey, if I ever take too long and I'm too slow, either bump up the time speed or just skip ahead. Yeah? I like to take my time in these videos because I'm just having fun. Okay, let's move on. So this is just understanding what the inequality means, right? So what does it look like in what's called set builder notation? Well, a set is denoted, or I say not with, but by curly brackets, like so. Look at this. I'm going to go back to the other side. Look at this. Remember how I said that earlier? A is a set. See the curly brackets, right? That's a set. It's a collection of items. And so set notation, I use these little curly brackets. So every time you do set builder, you're going to say, here's a curly bracket, here's a curly bracket. Okay? That establishes we're talking about a set. Now, within this set, we're just going to describe what the relationship with H is. So when it comes to set notation, there's really just two pieces. First, I wish you could see me because I'm using one finger to point into the air. First, set notation indicates what variable you're talking about. And then second, it's just the relationship with that variable, or I should say the conditions on that variable. So look at this, right? What's the variable in question? It's H, yeah? H is the variable we're talking about. And the relationship with H, I'm going to put this off to the right here, is that H is less than or equal to 10, but it's more than 5. And I'm going to separate these with a little bar like this. You say, okay, what? Say, okay, here's how you read this, okay? This is the set, and I know this because of the curly brackets, of H, because of this guy. That little thing tells me what variable I'm talking about, right? What element. The set of H such that 5 is more, or, H is more than 5, but less than or equal to 10. Okay? That's how you say that. The set of H such that H is between 5 and 10. That bar that I drew here means such that. It's like a substitution for the word. Okay? It's very common practice. You might also see colons. You might also see colons instead of a bar. It's interchangeable, doesn't matter. And you'll notice that the difference between set builder and inequality is just that you add those curly brackets as a set, and you kind of put the variable at the forefront to tell the reader what the variable we're talking about is. Okay? Now, interval notation. What's that about? So I'm going to come over here, maybe in blue. I'm going to say interval. I'm going to move this. Boop. Interval notation. And so things about interval notation. I say it uses parentheses and it uses brackets. Okay? So interval notation is going to use parentheses and brackets in any combination. So for example, it could be, I'll say example, bracket, comma, parenthesis. Okay? That can happen. And interval notation, what you want to look at is you want to look at your lower bound, comma, your upper bound. Now, what do I mean by that, right? Lower bound, comma, upper bound. And I'll just use like parentheses here, okay? Well, let's look at the example that we're given over here, right? So you see how H is stuck between two numbers, 5 and 10. And I haven't shaded past 10, and I haven't shaded before 5. H is inside here, right? So the lower bound on H, this is 5. This is the lower bound. It's a boundary. That's when we say bound, it's a boundary point, right? H does not go past 5. It doesn't actually even hit 5. But 5 is the lower bound because that's where it's approaching. It's near 5, but it go past it. 10, because it's more, 10 is called the upper bound. So the upper bound. All right? And so what I'll do over here, right? So interval notation, it's just lower bound, comma, upper bound. So the lower bound is 5, comma, the upper bound is 10. That's it. It's 5, comma, 10. But I told you that it uses parentheses or it uses brackets or a combination of those. And what do the parentheses and brackets mean? Well, if I come back up here to inclusive, not inclusive, that's what those are. So inclusive are brackets. Not inclusive are parentheses. And that's the difference, okay? If it includes the point, if it's equal, then we use brackets. But if it's not equal, it's strictly greater than or strictly less than, then we use parentheses. And that's it. That's the difference. So when I look at this point here at 5, I see that it's an open circle, which is not inclusive. So I'm going to use a parenthesis. So I'm going to come over here and say parenthesis here. And then this is 10. And that's filled in, which is inclusive. So I'm going to use a bracket. And so I put a bracket here. And that's what that means. An interval notation tells you an interval, a region, right? It's the space between 5 and 10. It's everything in between. And you've just given a lower bound and an upper bound. So you know what it covers. Yeah? Then we just use parentheses or brackets for inclusive, non-inclusive. Done. I love interval notation. I hardly use the other two ever. I love interval notation. Get familiar with it. You're going to want to know it. And yeah. If you truly want to experience what the lesson was like in class, I would pause this video and I would do this stuff, okay? Do all of this on your own and then check your answers in a minute, okay? But I'm going to go ahead and fill it out just because I want you to have the notes. And then I'm going to finish off with this little thing. I don't know how long this video is becoming, but I don't care because I like to take my time. And like I said, I'm having fun. Okay. So I'm just going to walk through it. So we see the interval here, bracket 5, comma 10. So the lower bound is 5, and it includes 5. And the upper bound is 10. So set notation, I just have these curly brackets. We're assuming we're just going to keep using that letter H. So I'm going to say H again, such that, well, H is between 5 and 10, right? You think, okay, here's H. The upper bound is 10, because it's got to be less than 10. But the lower bound, it's got to be more than 5. Thing about 5, though, is it's including that, so we say it's equal to. And that's it. It also kind of follows here. But see, inequality and set builder, you see how similar they are? They're basically the same thing, right? I go on to the next one, right? If I just drop that stuff, that's inequality notation. Like so. Notice what my upper and lower bounds are, right? H is still, again, between 5 and 10, but 5 is not inclusive. So, and neither is 10. So not inclusive is parentheses. So parenthesis 5, comma, 10, comma, parenthesis. Done. Now the next one's a little interesting. So I say H is less than 10. I'm going to change to yellow here. I wish I had more space, but that's okay. Let's do H is less than 10. So I'm going to make a little number line. Okay, I'll star this. I'm going to make a number line, like so. Boop. What does it mean to be less than 10? Well, here's 10. H is less than 10. That means it is behind it. 9, 8, 7, 6, 5, 4, all the way and keep on going, right? Does it include 10? No. So I'm going to use an open circle like this because it's not equal to 10. Yeah? Now, set notation is to be pretty easy. I just establish set H such that H is less than 10. Perfect. Beautiful. That's great. But how would I do this for interval notation? Let me bring this guy over here. So I have some more space to write. Now I say, what's the upper and lower bound, right? What are the uppers and lower bound on this thing? Well, 10 is definitely the upper bound, right? It's the maximum, right? It's not going to go past 10. But where's the lower bound? It's just going to keep on going and going and going, right? It's going to go on to the left forever. So this is really no lower bound. We call this unbounded. We say it goes towards negative infinity. Think about that, right? It's going on and on and on forever in the negative direction because it's going to the left. Right? Even if it was 9, 8, 7, 6, 5, right? It was all that. Eventually it's going to hit 0, and then it's going -1, -2, -3, where it's going to keep on going. It's unbounded and goes towards negative infinity. So the lower bound, there really isn't one. And so we call that negative infinity. So I say this is from negative infinity up to 10. Now, 10 was not inclusive, so I use a parenthesis. The question is, do I do a bracket or parenthesis for negative infinity? Well, infinity is a concept, not a number. And to be inclusive, that would mean to include a number, and infinity is not a number, and it is unbounded, so it's not including that. Okay? It's just a direction. So I just always, anytime you have a infinity symbol, it's just default parenthesis. Never bracket. Okay. I hope that's helpful. Switch to red back here again. So, if I reverse it, if I say bracket 10 to infinity, well, that's just saying, if I draw a number line, right, here's 10, and 10 is the lower bound inclusive, and infinity goes on just to the right beyond, like so, right? That's bracket 10 to infinity. So as a set, this is h such that h is more than 10, because it's greater than 10. But it includes 10, so it's equal. Right? It's like saying h is greater than or equal to 10. Yay! Nice. Okay. And now the last one, a little set thingy here. What does this mean? And so a lot of people in class got stuck on this because they've never seen this R symbol before. And that's okay. Because, like I said, we're building our mathematical vocabulary. That symbol R, let me do this in green. Lots of colors, right? This guy right here. Let me just star it. I don't want to circle things. Star. This double-legged R. Well, I guess in the math type, it doesn't look like a double-legged R, but what I just drew there, this little R, means the set of real numbers. Okay? That's it. It's all real numbers. That's what it is. It says ARN. You remember putting that for Algebra 1? All real numbers. So all that says right there is H such that H is in the set of real numbers, right? Remember that that's just in, right? Or part of, like I said earlier, right? H is part of the real numbers. H is a real number. No restrictions. No restrictions. So if H is a real number, it could be anything, right? I could draw a number line like this, and you see H could be anything. It could be here, it could be here, it could be here, it could go all the way out here, it could go all the way out here. The set of real numbers right here, it's not bounded. It has no upper bound and no lower bound. It extends to negative infinity towards the left, and it extends towards positive infinity on the right. And so whenever you see parenthesis negative infinity, comma, infinity, that means all real numbers. This is another way of writing that. Okay, and over here you can just say h is a real number. Okay, so that's that one. Now, I have one more, and I realize I probably should have left y'all even more space, but alas, I have not. And the next one I was going to create so that you could see. How do I want to do this? Give Mr. Spake some think time. Here's what I'm going to do. I'm going to say, for the purpose of these notes right here, see next page. Okay? I'm gonna go over to the next page. Oh. Uh-oh. Hold on. I wanted to add a page. Oh no, now I'm wasting video time. There it is. I want to add hello. Add. Oh my God. Add a blank page. Wow, why did that take forever? Okay, here we go. Continued. So I'm going to show you one more type of set, okay? Suppose, let's say, let's look at, I'm still going to use 5 and 10. So suppose h is less than 5 and, the better word actually, or h is greater than or equal to 10. What does that look like on a number line? So I'm going to make a number line here, like so. Boop, boop. So here's 5, and here's 10. Now, let's just look at h is less than 5 as an interval, right? If h is less than 5, it's not inclusive, so it's going to be an open circle, and it's going to be shaded to the left, right? It's going to be going this way, shaded to the left. That is h is less than 5. Now, if h is more than 10, inclusive, it's equal, it's going to say, okay, this is a filled in dot because it's equal, and it's more than 10, which means I shade to the right, like so. And it keeps on going, right? And this is what's meant by h is greater than or equal to 10. Now, these are two separate intervals. But when we talk about sets, right, a collection of items, we might want to join these two things. So you see, these are called two disjoint sets. These are two, I'm going to write that down, two disjoint, oh my God, I can't spell, two disjoint sets. Okay? Disjoint means not connected, right? Separate. They're separate sets. So in interval notation, we have two things going on here. The first set is h is less than 5. You see, h is less than 5 is the interval. I don't write this extensively in class, but I told you, these videos are more in depth and slower. Yeah, h is less than 5 is the interval. Well, upper bound is 5. It's unbounded on the left, so it's from negative infinity to 5, not inclusive of 5. Parenthesis. Yeah, and h is greater than or equal to 10 is the interval. Well, it starts at 10. It's a lower bound. Bracket 10 goes to positive infinity. And like we said, infinity is never bracket, like so. So we join these two sets with the union symbol. And that is u. Okay? So, looks like... So here's what the interval actually looks like. It's from negative infinity to 5, unioned with bracket 10 to infinity. What does it mean to union something, right? Union is to put together, right? To, if you think unions, right, to organize where all the workers come together, they band together against their corporate oppressor, right? You're unionizing against something. Union means to join. And so we join these two sets with a union operator, which is the symbol U. Okay? It's specifically this curved symbol. It's not like a capital U, okay? Sometimes I see students do this. Oh my gosh, please no. Okay, that's it's not actually the letter U. It's actually its own symbol that's a U shape, okay? And the reason this is there's actually an opposite one that looks like this. I'm not going to talk about that right now, but there's another one that looks like that, and that's not a letter, right? It's just a hump. It's literally just a hump. So put that hump there, okay? There you go. And this is, right, so this is inequality, right? This is inequality. And then down there is interval. So if I go over here, right, the interval was negative infinity to 5, unioned with bracket 10 to infinity, right? And the way I wrote that as an inequality was h is less than 5 or h is greater than or equal to 10. And since set builder is just inequality notation with the variables established, it's just h such that h is less than 5 or h greater than or equal to 10. Done. And so that's the word about union. Yeah. I know I've kind of taken my time on this, but if you can have this down, if you can just get solid on this, it just helps so much. It makes reading the math easy, all right? It's what you're doing is you're building your mathematical literacy. You are getting good at reading math. And so when you see problems, when you get asked a question or you see answer choices to choose from, having this strong foundation and reading these sets and these intervals, you can actually make sense of what's going on, okay? Yeah. Okay, interpreting domain and range from a graph. This is the last piece for the video. Boy, I sure do talk a lot in this lesson, huh? Okay, interpreting domain and range. When interpreting the domain and range of a graph, pay attention to 3 important characteristics. The first characteristic is discontinuities. Discontinuities. This is where the graph has a break, okay? I will say this. It's where the graph breaks or where it has a hole, okay? Holes and gaps. Oh my gosh. I'm so sorry. I should... Holes and gaps in the graph. Okay? That's what a discontinuity is. So what's an example? Actually, example 2 is perfect. Okay? A function is continuous on some interval if it never breaks. Okay? If I can take my pen and stroke some curve, right, without ever lifting the pen, that's continuous. But if you notice this curve I've plotted here, I'm drawing it here, but then, I have to lift my pen and then jump over here. Yeah? I did it, if it was one fell swoop motion, now, hey, that's continuous, but this point right here, that's a discontinuity. Discontinuity. That's what that is. And this empty space is a gap. And also, another word for discontinuity is whole. So that open circle that we were seeing, you're going to see open circles on graphs. They mean the same thing. It means don't touch. It means you get close to but don't touch. That's a discontinuity or whole. Okay? The sooner you know that vocabulary, the better. We're going to talk about wholes a lot in the second semester. Okay, the next piece is asymptotes. Asymptotes. Tote. Oh my gosh, I hate my T's. Okay, what's an asymptote, right? A line, the curve approaches. Curve approaches. If you took Algebra 1, well, I mean, you did because you're in this class. But taking Algebra 1, you often learn that asymptotes are a line that a curve approaches but does not touch. I'm going to leave out that does not touch stipulation because that's actually incorrect. All right? That's actually not always true. And so if it's not always true, it's not correct to say that as part of the definition. Yeah? When you learn it in Algebra 1, they never touch. But in Algebra 2, you're going to see asymptotes where you actually do cross the asymptote. However, you can think of it as not touching still. We're not to that point in the semester yet. We'll get there. But if you want to keep on to that idea that it doesn't touch, hey, by all means, do that. We'll talk about it later, okay? Anyway, if it doesn't touch an asymptote, it helps you kind of figure out where the graph is going. It tells you what it's approaching, right? And then the last one is end behavior. End behavior. And so what is end behavior? Well, as x increases, so as x goes to positive infinity, where does y go? Right? Does it approach a number? Does it go up to infinity, down to negative infinity? And then the same idea is if x goes to negative infinity, where does y go? And that's pretty much what end behavior means. Okay? So you're looking at the ends of the graph. You look at like if I'm looking at this graph right here, the end behavior is what's going on out here and what's going on way out here as I go off to the right. Yeah? That's end behavior. Okay. And so if you observe these three things, holes and gaps in the graph, asymptotes where a line gets close to something, or when the graph gets close to a particular line, and end behavior, how it's behaving at the ends, that's going to help you figure out what's going on with the domain and range. Now, from Algebra 1, you should remember domain is x. We read that left and right. So if you look at this graph here, right, pay attention to your x-axis here. You know what? In fact, I'm gonna label it, right? This is the x-axis, and the curve is defined. It goes, you see this arrow implies that it keeps on going to the left, right? So it's this piece of the x-axis, and the curve is still defined. It's still defined. It's still defined. This arrow implies it's still going to the right. And so it's still defined. It goes on and on and on and like this. Essentially, you have shaded in the entire number line. So what's that interval, right? I'm going to do interval notation, negative infinity to positive infinity. That's the domain. Now, erase this. Okay. I'm going to switch to blue. This is this blue line is the range, okay, or is the y-axis. Now, what I want you to notice is that this line is getting really, really close here to this value, but that's an asymptote. And this is an asymptote we're actually not touching. So I'm going to use a dashed line here because it's an asymptote. asymptote. And actually, in particular, is y equals -3. So anyway, that's our asymptote here, and that's kind of telling you where the lower bound on y is. Because if you remember, we read range up and down, right? So your y's are kind of at this asymptote, and then they go up and up and up, right? Up, 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 all the way. And that's why, right? You see, because this arrow means it's going up. This arrow means it's going, well, down to this line at the asymptote. Okay? Does that make sense? I hope it makes sense. If you just look at this graph, right, if you're reading vertically, up and down, up and down, up and down, the lowest point is here at the asymptote, y equals -3, and so that's the lower bound. But the upper bound, well, it just keeps on going up and up and up to infinity. It's unbounded. So I say the range starts at -3. It doesn't touch the asymptote, so it's not inclusive. And then it continues up to infinity, like so. Okay? Okay, let's do example 2 now. So example 2, remember domain is x, right? I should put these x and y, x and y. So domain, look at my graph here. So if I read it left to right, it starts here, it's a filled in point, and it continues all the way to right here where there's a hole. Well, what's that interval? I mean, that's literally on the number line, right? The lower bound is at -5, and then the upper bound ends at -1. And if you pay attention to the filled in versus the open, right? It's filled in at -5, so it's bracket, it's included, it's inclusive. But it's a hole or open circle at -1, which means parenthesis, not inclusive. Now let's look at the other one. The graph then now is going to make a gap. It's going to skip, and it's going to start right here at 3, and then it's going to continue on to the right. And it's going to keep on going forever. So you see this is -5, it's -1, that's 3. And it's going to go on forever to infinity. So the next interval is bracket 3 to infinity, unbounded above. And remember, how do I join these two intervals together? I use a union symbol. The union connects these two. All right? Now I look at the y values. So the bottom here, right, this arrow implies it goes down to -infinity. So it's going to go down and down and down and down, all the way to -infinity. It's unbounded below. So the lower bound we call -infinity. Now let's trace this, right? It's going all the way down forever, and we're going to follow the function up like this, right? And we're going to keep on going up, 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 and we get right here at 1, right? That's 1, and it's filled in here at 1, but it's an open circle right there. Because it's filled in, this guy, that's included, okay? You say 1 is included. I'm going to point to this. 1 is included in the range. That's what that filled in point means. And then if you continue along this curve right here, right, you're going to keep on going up, 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 but finally it's going to stop here at 4. And so if you're looking at my y-axis, right, 4 is up here, and it goes down to -infinity. So your upper bound is 4. And it stops there with a nice inclusive bracket. That was awesome. I love that. Wow, look how colorful. Oh my gosh, it's so pretty. It's so pretty. Okay, so if you had any struggles on the day one, the first day of class. I know it's kind of a lot. It's interesting. It's like simple, but also not, right? It's very basic foundational stuff, but there's a lot of nuance to it, right? There's a lot of vocabulary and reading and interpreting and understanding what we're looking at. Like I said, in this lesson, we're really building that math literacy. We have to be able to read math and interpret the symbols before we can really do math, yeah? You can't write an essay until you can read one, if that makes sense, right? How can I write sentences if I don't know what a sentence is? Anyway, that's it for this video. I hope that this was a strong, good explanation. I hope I was not too confusing at any time. If you have any questions, ask me in class. If you're just some random person on the internet somehow that has stumbled across this YouTube channel, leave a comment, because I appear to be getting more viewers that are not just my students. You're welcome to comment, and I will try to check the video and see. I hope these explanations were sufficient. Anyway, there it is. Hope you enjoyed, and thanks for being here.